So now we've got a whole chapter on alcohols. And the hallmark of an alcohol here is that you've got an OH group. We call that a hydroxyl group. And having an OH bond, you are capable of hydrogen bonding as an alcohol. And as a result, it's going to affect the physical properties here, both solubility as well as boiling point. Now, if we look at solubility in water, water has hydrogen bonding, is very polar, and so your small alcohols tend to be very soluble in water. So if we look at ethanol here, a 2-carbon alcohol, it is completely miscible in water. And that means you can mix it with water in any proportion. Once you go to butanol here, though, no longer miscible, but still a rather high solubility at 73 grams per liter. But go up to 6 carbons here with 1 hexanol, and we're all the way down to a solubility of just 5.9 grams per liter. And then actually go to 1 octanol, and rather insoluble here with only a solubility of 0.3 grams per liter. So the short chain alcohol is fairly soluble in water, but increase that chain and it gets progressively less soluble in water. We can also take a look at that boiling point here. And for the boiling point, hydrogen bonding is a rather strong intermolecular force, and so as far as molecular compounds go, alcohols have rather high boiling points compared to compounds of similar size that don't exhibit hydrogen bonding. So if we look at 1-butanol here, it's got a boiling point of 118 degrees Celsius, but if you compare that to either 1-butanal or diethyl ether, both of which are not capable of hydrogen bonding on their own as a pure liquid, boiling points of only 75 degrees Celsius and 35 degrees Celsius respectively. So considerably lower since they don't have hydrogen bonding like 1-butanol does. So big thing about alcohols again, hydrogen bonding and how it affects both boiling points and solubility here. Just a little intro. Let's talk about how to name them. So I'm talking about naming alcohols. It turns out there's a couple of different situations. It can be one of, it can be the main functional group in your molecule, or there could actually be a more important functional group, and so in that case you just name the alcohol as a substituent. And up until now we don't have any more important functional groups in the rankings than alcohol, so we're just going to stick with naming them as a functional group, but we'll come back to that as a substituent later on in the course. First thing you want to do is find the longest continuous carbon chain the OH is attached to. Notice this may not be the overall longest carbon chain, just the largest one the OH is attached to. If we look at this one here, we've got a carbon here, a carbon here, a carbon here, and a carbon here. And so the longest continuous chain the OH is attached to is 4 carbons. We're now going to number this chain to give the OH the lowest possible number, so we'll number it right to left, so 1, 2, 3, and 4. And we're going to use the OL suffix, so OL for alcohol, at the end of the parent chain. Now in this case we've got no substituents, but we'd name those first just like we do with alkanes and alkenes and alkynes. But in this case this is just simply 1-butanol, or you can put the 1 right before that suffix all. We'll find out later on when you've got multiple important functional groups. Oftentimes you're going to have to stick numbers in the middle of words. We saw that a little bit with alkenes and alkynes. We're seeing it again here. In fact, if we had an alkene or an alkyne with the alcohol, we'd be forced to put numbers in the middle of the word. But in this case, with only one major functional group, the alcohol, we can put the 1 before the parent chain or in the middle of the parent chain. In this case, let's go to a cyclic one now. Now with the cyclic one here, we've got a 6-membered ring, and that's going to be where the OH is attached. That's going to be the major parent chain here. And in this case, where you start as 1 is totally fixed based on where the OH is. It doesn't matter where any other substituents are, because they're just substituents. The most important thing is the OH. And so this automatically gets to be carbon number 1. Now in this case, it's not going to matter, because whether we go around clockwise or counterclockwise, we're going to end up over here at this carbon with the other substituents at number 4. And so it's arbitrary, but if one way numbered faster towards this other substituent or give them a lower number, that would be the way you'd choose. But in this case, 1, 2, 3, 4, 5, and 6. So in this case, we do have substituents. We name those substituents first, just like we do with alkanes, alkenes, and alkynes. And in this case, we've got a methyl group at carbon 1 and another at 4 and another one at 4. So we've got 3 methyls. So we've got to give 3 locations. We're going to say 1, 4, 4 hyphen tri methyl. Now, because this is cyclic here, the OH was automatically by default going to be chosen to be on carbon number 1. And because the OH has to be on carbon number 1, we are not going to include that in the name. It has to be there. So for a cyclic alcohol, the OH is always at carbon 1, so it's not part of the name. So in this case, 1,4,4-trimethyl cyclo, don't forget the cyclo, hexanol. If you said 1,4,4-trimethyl 1-cyclohexanol, it's technically wrong. You're probably going to lose half a point or something along those lines. So again, on a cyclic alcohol, don't include the 1.